Swayam Prabha. Digital India. Educated India.
Namaste and welcome back to the video course on watershed management. In module number 6, in use of modern techniques in watershed management, lecture number 25. Today we will discuss about integrated watershed modeling using numerical methods, GIS and remote sensing. So, in the last few lectures we are discussing about the geographic information system, remote sensing, decision support systems and its applications. So, in today's lecture the topic is how we can utilize this geographic information system, remote sensing and numerical methods which we have discussed in some of the earlier lectures. So, how we can use in an integrated way, and then what are the difficulties, what are the advantages, then how we can apply for say specific case studies. So, like that today's lecture is put. So, some of the topics covered include integrated watershed modeling, numerical methods, finite element method, computer modeling, geographic information system, remote sensing and applications in watershed management. Then for today's lecture the keywords: integrated watershed modeling, numerical modeling, geographic information system and remote sensing. So, as we were discussing earlier, so watershed management is a very complex process. We need to consider various systems related to land, water, then human being, then the flora and fauna within the area. So, that way so we have seen that to study, to predict what will happen if some specific projects are implemented, to study what will happen, we have to go for modeling, and then we have to understand the system in an effective way. So, that way, say for example, when we are dealing with water, so we will be discussing about rainfall to runoff modeling. So, that way when we are going for rainfall runoff modeling, so as we discussed in some of the previous lectures, we have to consider all the hydrological processes at various levels, and then we have to model these processes, and then in this way we need a huge quantity of data, say geographical data, topological data, topographical data, climatological data, like that. So, when we have to use all this data, and then we are going for modeling, say in a prediction mode, to simulate say what will happen within the system. So, that way if we can integrate say the computer models like numerical models, which is generally used for rainfall runoff or sediment yield or erosion type models, and then we combine together this type of models, hydrological models or other kinds of models, with geographic information systems and remote sensing, which gives a good database. When we can combine, integrate together these modern tools, then we have an effective tool which can be used for watershed modeling or watershed management. So, let us look say some of the important points which we have discussed earlier also. So, here in this slides I have kept the necessity of integrated catchment or watershed based modeling. So, as I already mentioned, say water resource management, say generally we do catchment based or watershed based, and then say when we deal with watershed based or catchment based planning and management, we have to deal with a huge amount of data, and then we have to see the variation, spatial variation, temporal variation. So, say as we discussed, say rainfall runoff modeling. So, we need to assess how much will be the runoff within the watershed, say for the given rainfall conditions or for the possible rainfall conditions, or we may have to assess, say what will happen if if we consider the effect of climate change, or what will happen if the soil loss or erosion problems is exceeding certain limits. So, all those studies we need to have an integrated approach. So, modeling, say most of the time, say as we discussed earlier, modeling can be either simply black box based approach or empirical approach, or say lumped approach or distributed approach. But we can, as we discussed earlier also, the distributed based modeling or physically based models based upon the physical laws of conservation of mass, momentum and energy, these kinds of models are very essential to see what will really happening within the watershed or within the area, say for the given conditions. So, these kinds of physically based models only can predict, say so the variations with respect to spatial or with respect to temporal for the given condition. So, that way the models based on physical laws are very important and necessary in the case of watershed modeling. So, we need to go for an integrated catchment or watershed based approach, say while dealing with various problems related to water or soil or land or the sustainable development of the system. So, if you consider water or hydrological aspects of the hydrologic processes, we have to consider like infiltration, then evapotranspiration, runoff, then groundwater component, etc. So, if you consider the last 50 years development in this area. So, earlier say before 1960s or 1950s, say it was so difficult to do these kinds of say studies say in a comprehensive way, say since the area which we are considering is large, and then we cannot develop physical models or laboratory based models, or to go to the field and then take the measurements. All these things were so difficult. So, that way, and say when this due to the digital revolution which has taken place last 50 years, say huge changes have taken place in the area of this say these kinds of modeling. So, with the development of the computer technologies, say modern numerical techniques like finite difference method, finite element method, etc. came to picture, and then that way the solution of various hydrological processes or hydrological modeling became much easier and much faster and much more comprehensive. So, and then as I mentioned, when we deal with these kinds of modeling, we have to deal with the huge data set. So, this data set which needed for these kinds of modeling we can obtain from the geographical information systems or remote sensing, which we have discussed in the last few lectures. So, that way the recent advances in watershed modeling is the use of combined or integrated approach of numerical modeling, remote sensing and GIS. So, that already the large development have been taken place in this area, and then now sophisticated models are available say for the integrated watershed or integrated water resource management approach. So, here I have shown a flow chart where say how we can do integrated watershed modeling approach. So, first step is we have to identify the specific problem. It can be hydrologic problem, or it can be soil erosion problem, or sediment yield problem, or whatever problem which we are trying to do as far as the watershed is concerned. So, that we can identify, and then for any of these kinds of studies we need say good amount of data. So, we can have we can set the geographic information systems based upon the available data, the topo sheets and other maps. So, next step is design of the geographic information systems like data layers and attributes, and then of course, to identify the variation say taking place for the watershed spatially or temporally, we can use the remote sensing. So, the second step here as shown in the slides is the use of GIS and remote sensing in an integrated way, so that we are having the database. So, the based on using the GIS and remote sensing we can develop the database. So, database building, and then this data can be processed in different ways. So, that the way which we needed, like various maps like deep elevation models, land use map, slope map, land cover map, soil map, etc. we can make. So, this is the third step where database and data processing can be done within the environment of geographic information systems and remote sensing. And then next step is either we can develop the hydrologic model, or we can select the hydrological model and then say a formulation using numerical methods. So, we can select the approach which we are doing through conceptualization, mathematical modeling, and then either we can choose appropriate hydrologic model, or we can develop our own model based upon the needs for that particular problem. So, then say once the model is chosen and then or the model is developed, and then as we discussed earlier, we have to calibrate and validate. So, all those things are needed. So, then we can go for the model computations. The next step is model computations. So, as shown in this case, the fifth step is model computations, and then we can based upon this model computations or simulations, we can compare the results, or we can generate various scenarios or various alternative plans and then study in detail. So, that way an integrated approach of geographic information system, remote sensing and hydrologic models or numerical methods, a basic structure can be like this, and then we can integrate together, so that we will be having an effective tool for the particular problem which we consider, whether it is rainfall runoff modeling or hydrologic modeling or soil erosion modeling, or what kind of studies which we are planning say for the particular watershed which we are considering. So, now when we are dealing with hydrologic and hydraulic modeling, so here I have put a slide which we have discussed earlier also. Say for example, rainfall to runoff. So, two aspects is there. First one is hydrologic modeling and then hydraulic routing or hydraulic modeling. So, we have to start with the problem like say to assess the runoff within the watershed. So, that is a problem definition for the given rainfall condition, and then we have to conceptualize the model, say like overland flow, channel flow, like that, whether one dimension, two dimensions, and then we can develop the mathematical model, and then we can choose the numerical model, and then based upon that numerical models, say this numerical model can be like tools like finite difference method, finite element method, etc. And then based upon that we can have the computer model, and then we have to go through a process of model calibration or verification, and then we have to assess the model adequacy. So, this is the first part, and then second part, say we have to collect the field data, then say we have to compare the field data and assess the field data, and then once the model is constructed, we have to go for the performance or criteria evaluation, then calibration validation, and then model predictions, and then sensitivity analysis, results and discussions, and then post audit analysis, or and then further cross checking with the field data. So, like that we can do the hydrologic or hydraulic modeling. So, here also as I mentioned, we can integrate the system like geographic information systems and then the remote sensing data for such kind of integrated modeling. So, as I mentioned earlier, say most of the time we need to go for physically based modeling, since that is very important, since that gives how the system is behaving spatially and temporally, and then we can study what is happening say minute wise or hourly wise, or the way which we want. So, that way say for example, when we are dealing with rainfall to runoff. So, here this particular flow chart shows say for event based rainfall runoff modeling. So, rainfall is taking place within an area watershed, and this is the overland flow, and then this is the channel flow, and then say the flow development takes place or runoff starts, and then infiltration also taking place. So, depending upon the model which we consider, we can have various components including the evapotranspiration, groundwater component, etc. So, a general concept of flow modeling say for rainfall to runoff is shown here. So, we start with the rainfall, then say the overland flow component we can simulate, and then infiltration we can consider, and then the channel flow basis, and then flow at the outlet of the watershed or particular location where we are looking for. So, that way we can develop the model, and then we can consider the physically based distributed model. So, physically based distributed model, it needs lot of data, and the modeling efforts are very high, but even though the results may not be so good, but it gives so much of physics of the problem, so that we can easily understand what is the mechanism taking place within the watershed, say for example, when rainfall runoff process is taking place. So, that way physically based distributed modeling is very important. And now say we are discussing about the integrated approach of numerical methods, GIS and remote sensing. So, say as we discussed in the another previous lecture, so remote sensing is one of the important tool used in hydrologic modeling. So, the remote sensing data are capable of solving the problem of scarcity of data. Since we need a huge amount of data, we can get this data from the remote sensing. Say for example, this is a remote sensing picture which shows the various land use, land cover, the channel location, like that. So, the importance of remote sensing we have already discussed in one of the earlier lecture. The advantage is that when the satellite is passing over particular watershed or particular area, we can identify, we can get the spatial variation at a stretch for the particular watershed. And then when again that satellite is coming back, we can consider say weekly basis or monthly basis or seasonal wise or annual wise, how the variation is taking place within the watershed. For say if you implement a project, what will be happening, or if the existing projects, what will be the situation taking place. So, like that the temporal variation we can easily understand with reference to remote sensing. So, that way remote sensing is very important in these kinds of modeling. So, as we have seen earlier, remote sensing mainly two parts. First one is the data acquisition. So, data acquisition is done through satellites or other say media like aeroplane or other systems, and then this data is obtained in the data center. Say for example, India National Remote Sensing Center located at Hyderabad is having all this data. And then once this data which is needed for the particular area, we can obtain through from that agency, and then we have to analyze the data, so that the area which we need, we can get the complete details say as a file which we can see in the computer and then analyze. So, that way remote sensing it has the capability of observing several hydrological variables over large areas on repetitive basis. So, that is the advantage of remote sensing. So, the capability of observing several hydrological variables over large areas on repetitive basis. So, that is the major advantage of remote sensing. So, then the other tool like geography information system, about this GIS also we had a discussion earlier in one of our earlier lecture. So, here what we do, we give the input say like the topological data or the available data in terms of digital form or other scanned form, and then this data is manipulated or transformed by various techniques within the software, GIS software, and then we get the output. Say output can be in various forms like maps, like land use map, land cover map, soil map, or digital elevation model, slope map, like that. So, that way the important components of GIS are the data input, then storage and management, data manipulation and analysis, and the data output. So, this shows a typical flow chart as far as the GIS is concerned. So, here data input for the system, then system data storage and management, then data manipulation and analysis, and data output for the system, and then everything is visible through a user interface or so called a graphical user interface. So, that way say as we have seen in the earlier lecture on GIS, so we can effectively utilize the system say, and then generate various maps say like we can delineate the watershed, and then also obtain the digital elevation model or slope map like that. So, that way GIS serves a major contribution as far as the hydrological or watershed modeling is concerned. And then next tool is the numerical methods or computer models. So, as we have already discussed earlier, say to simulate what will be happening within the system within a watershed, say for the given conditions, say like given rainfall conditions or give, say, when we are constructing a dam or a check dam or various, when or we are going for various rainwater harvesting measures, then what will happen as far as hydrologic processes are concerned within the watershed. So, this we can do only through simulation or modeling. So, the system is so complex. So, that way there is no easy solution or even exact solutions, analytical solutions are not available. So, we have to go for modeling. So, modeling can be like, as we discussed, it can be simple black box or empirical models or lumped models or the distributed models. So, especially when we are discussing with physically based distributed models, we have to solve very complicated partial differential equations like Saint-Venant's equations, as we discussed earlier also. So, that models say we have to run through the in computer, and then we have to say get the for particular say conditions, we have to run the model and get the results. So, that way numerical methods, as we discussed earlier, the steps are conceptual modeling. So, based upon the requirement or the objectives, we can develop the conceptual model. Then the mathematical modeling. So, we can obtain the governing equations, initial conditions and boundary conditions depending upon the problem. And then mathematical problems we solve, the models we solve by arithmetical operations or in computer. So, as I mentioned, due to the digital revolution, now the numerical methods we generally use for these kinds of problems, like a finite difference method or finite element method, which we have discussed earlier. So, computer models, as we discussed, a number of models are available depending upon the requirement, depending upon the necessity or the data availability or the computer facility. We can choose particular models either in 1 dimensions, 2 dimensions or 3 dimensions, and then we can go for depending upon our objectives, so particular modeling. So, numerical methods, as I mentioned, like finite difference methods, finite element method, finite volume method or boundary element method. So, like that number of methods are available as far as numerical methods are concerned. So, that way now when we go for integrated watershed modeling using the numerical methods, GIS and remote sensing. So, this shows a typical flow chart. So, for the first step is selection of the watershed or for the given watershed, which is a watershed, and then get to the necessary data, available data, and then simultaneously we can obtain the remote sense data through satellites and then develop a GIS database. So, then the data collection for watershed, so physical data collection like for the particular area, what kind of available data, or from the field we can collect various data, and then we can delineate the watershed and then prepare various thematic maps based upon the remote sensing data and the available data. Simultaneously, we can go for the mathematical formulation. So, we can decide depending upon the objectives whether we are going for a 1-dimensional model or 2-dimensional models, or whether we are going for the physical models or lumped models or black box models. So, like that we can decide. So, if we are going for, say, for example, physical models, then we have to solve partial differential equations in 1 dimension or 2 dimensions generally. So, then we can do the numerical formulations, and then we can develop the model. If you are going to build in your own model, then model development. Otherwise, depending upon your requirement, you can purchase the particular software, or we can download if it is freely available from the internet. So, then by getting this model is developed for the particular area, and then using this data, the available the prepared data set, we can say develop the model and then run the model. So, that way the next step is model output. So, once the model output is obtained, so as I mentioned, this is obtained through various processes like calibration, validation, since many parameters we have to determine through this process. And the next step is testing and evaluation of the model, and then for the particular conditions, particular watershed or particular area, depending upon the requirement, we can finalize the model. So, this way this flow chart shows a typical model. So, here as shown here, say various steps are shown here effectively. So, how we prepare a particular model as far as the watershed integrated watershed modeling is concerned. So, this flow chart shows the way which we develop the model. So, now say for example, as I mentioned, if we are going for the watershed base or if watershed modeling, say for rainfall to runoff, say we will be using if we are going to use the physically based model, say event based modeling. So, then we have to consider various hydraulic processes. So, here in the slides, so you can see the various steps which we can follow. So, here say depending upon the requirements, so these are the steps, the flow chart which I mentioned. So, here starting with the various database development, model development, and then evaluation and finalization of the model. And then if you are going for rainfall runoff modeling, so we can decide the infiltration model which we are going to use. Various models are available as we discussed earlier. So, like Phillips model, Greenham model, SCSCN based model, like that we can decide the infiltration model. And then overland flow is concerned, since this is we can have either one dimensional based model or two dimensional based model depending upon the data availability and the requirements. And generally the channel flow, when we are going for rainfall runoff modeling in watershed, we can go for one dimensional modeling. Then we couple all these processes like infiltration, overland and channel flow, so that we can get the runoff at particular location. So, in this case, so event based model, say most of the time we can neglect the evapotranspiration since it is done for few hours depending upon the rainfall condition. But if say sufficient data is available, we can consider other processes also like interception, interflow, then evapotranspiration, etc. for the particular watershed. So, that way we can go for the modeling. So, then as I mentioned, say at IIT Bombay we developed a model, physically based model for rainfall runoff modeling for watersheds. So, the details we are going to discuss in the coming few slides. So, here say we developed the one dimensional model, strip based model for overland, and then channel flows one dimensional say diffusion wave based, and overland flow was kinematic wave based model. So, there are various details we will discuss in these few slides. So, the infiltration has been modeled using Phillips infiltration model. So, to here the purpose to calculate the infiltration rate and subsequent excess rainfall. So, that is what we are trying to do. So, the rate of infiltration is given by in the Phillips model by this equation, and here F is the potential infiltration rate, and SI is the infiltration sorptivity, K is the hydraulic saturated hydraulic conductivity, and this infiltration sorptivity is given by this equation. So, here K is hydraulic conductivity, and then in this equation here you can see that Ks is the saturated hydraulic conductivity, SN is the initial soil saturation degree, and psi is the saturated matrix potential of the soil, then lambda is the porosity distribution, like that. So, that way this Phillips infiltration model, one of the commonly used model. So, the details are available in most of the textbooks or the web. And then say as far as overland flow is concerned, as I mentioned, we can go for two dimensional models or one dimensional model. So, the governing equations here in this slide I have kept. So, here the overland flow, if you are doing two dimensional modeling, the continuity equation is given by this equation, del h by del t plus del u bar h by del x plus del v bar h by del y is equal to r minus I, where h is the depth of flow and u bar is the velocity and v bar is the velocity u in x and y directions, and then r is the rainfall say intensity, and I is the infiltration rate. And then we have to solve simultaneously moment equation x direction. This equation gives the moment equation x direction. So, here SOX is the channel or the overland slope, and SFX is the energy slope. and then this is in x direction, and similarly we have to solve the equation y direction. So, where the equation is given here, and this energy slope here we can use the Manning's equation as given in this equation number 4 and 5. So, that way say these equations, if you are going for 2-dimensional modeling, we can directly solve these equations, and then we can get the output will be the depth of flow at particular location and the velocities in x and y direction at particular time step or particular location. And then channel flow is concerned, as I mentioned, generally we can go for 1-dimensional modeling. So, in for 1-dimensional channel flow modeling, we have to solve the continuity equation and the moment equation. So, continuity equation is given by del q by del x plus del a by del t minus q is equal to 0, where q is the discharge, t is the time, a is the flow cross section area, small q is the overland flow component coming to the channel, and that we have to route. And the moment equation 1 dimension is shown by this equation number 7. So, which is del q by del t plus del by del x, so q square by a is equal to g into a into s minus sf minus g a into del y by del x, where sf is the energy slope, s is the channel slope, and g is the acceleration due to gravity. And then sometimes depending upon the requirement, we can also combine this overland flow and channel flow model with a groundwater flow model if there is interaction is expected between the components, or if you want to go for further comprehensive modeling. So, governing equation for groundwater flow in 2 dimension is given by this equation number 8, del by del x of k x h in del h by del x plus del by del y of k y h del h by del y plus I x by t minus s del h by del t, where h is the hydraulic head, k x and k y are hydraulic conductivity in x y direction, I is this is the infiltration or the inflow coming to the system, s is the specific yield or storage coefficient depending upon the system. So, as I mentioned, at IIT Bombay we developed a 1-dimensional model for overland flow, 1-dimensional that was kinematic wave based, and then channel flow using diffusion wave based model. So, the details are given here in this slide. So, here we use the finite element method to solve these governing equations for continuity and moment equation. So, here the say the kinematic wave or diffusion wave, the continuity equation is given by this equation. So, earlier equations what we considered is the continuity equation and the moment equation at the full form of the Swayam equations, but here the diffusion wave or kinematic wave are simplified forms of dynamic wave or the Swayam equation. So, the moment equation, when we consider the bed slope is equal to energy slope, that form is called kinematic wave form. So, this equation, and we consider the continuity equation, and then when we consider del h by del x is equal to s 0 minus s f, that equation plus this continuity equation when we solve, then that is the diffusion wave form of the Swayam equation. So, in the model we developed, we solve these equations using the finite element method, using the Galerkin criterions, which we discussed earlier also in one of the previous lecture. So, we approximated this equation by using this condition, also using the shape functions, linear line elements, and then 1-dimensional model has been developed. So, this shows the finite element system of equation, and the diffusion wave, if you want to use, this can be approximated like this and then keep it in the model. So, we can have the either kinematic wave model or the diffusion wave model for the overland flow component, and then this overland flow will be joining the channel. So, the channel flow is also modeled as 1-dimensional flow. So, here we have to solve the continuity equation given by this equation, and the kinematic wave form for the channel flow, again we substitute Betz